Okay, so what we are going to do today is to look the design of the controller in the frequency domain. Okay, so what we are going to study the frequency domain analysis for control system, and here we are doing the design via frequency response, and today is December 16. Okay, so this is what we are going to study today. So before we do that, I want to make sure that you understand the important uh, performance indices here for while doing frequency response. First, I want to remind you that the control problem basically it is solving 1 plus k g gc equals 0. So this is the what we call the characteristic equation of the closed loop system, and this is what we are trying to solve. And when we are talking about the control specification, phase margin and gain margin, it is related to this. Now, the frequency crossover frequency, it is the frequency at which the magnitude is equal 1. And here we are talking about the magnitude K, G, GC equal 1. So this is the magnitude, okay, and the corresponding frequency at which this magnitude equal 1, we call it frequency crossover. Okay, so crossover frequency is this frequency. So when the magnitude plot crosses the 0 dB line, this is the frequency crossover, and you will get questions, and I probably show you examples of the questions that were asked in the final exam on this issue. Second, you need, so this is an important term. If you don't understand it and you don't understand what it means, as I say it, you are lost. You won't understand what I'm talking about. The second thing that we did define is the gain margin. And here the gain margin is defined, it is K of this relation such that the amplitude K, G, GC equal 1. Okay, K times G times GC equal 1. The value of K that makes the magnitude K, G, GC equal 1, okay, it is the gain margin. So where the phase angle is minus 180 degrees. So we look at the phase plot. We find the crossing of minus 180 degrees, and we project it on the magnitude plot. We find the gain, how much gain we can increase to get the gain, the GC equal 1. Okay. Example. So if I want, I think I can do. I want to use, probably I should insert empty slides here. Okay, let me do that. Let me insert empty slides so I can use. I can use this as scratch paper. Okay, so let me go back here. So what do I mean here? Okay, so what I mean here is the following. So if I have a system, and this system, I will do an arbitrary system here. Okay, and so this is my system. Okay, so I have the magnitude plot. So this is the magnitude plot. This is the 0 dB line, and this is the log of omega over omega c, whatever. Okay, so this is the let's say this is 0.1, this is 1, this is 10, and this is 100. And here we have minus 20 dB, minus 40 dB, plus 20 dB, plus 40 dB. And suppose I have my plot is something like this. Okay, my magnitude plot, and I have a phase angle plot, which is okay, this is 0 dB, 0 degrees, minus 90, minus 180, and minus 270. Okay, so this is well, I don't know why the minus 180, which is this is what we want. It's not drawing. Okay, and okay, anyway, you know why? Okay, so let us assume that the phase angle is our phase angle something like this. Okay, and so here my minus 180 line. So this is the minus 180 line. Now, so this minus 180 line, I go here and I find, okay, so I find this is the crossover phase crossover frequency. I project it up here. Now, where is the gain margin now? Yasmin, where is the gain margin? You always, by the way, you are not in the class. I don't know why, and okay, but I need to, okay, where is the gain margin? Where, show me on the graph where is the gain. It is this distance, right? It is this value. This is the gain margin. Is the gain margin positive or negative in this case?
Positive.
Negative. Why negative? Because we have to reduce the gain to make, we have to bring this curve, the magnitude plot, we have to bring it down. I have to reduce the gain. So if I want to, okay, I have to bring this system down to make this, okay, zero gain margin. And if I want to a positive gain margin, even I have to reduce it down. So I have to reduce the gain to, so if I want a gain margin which is reasonably positive gain margin, so I want to bring the, I want the magnitude plot to be this line here, and this okay, this system is unstable, therefore so this is what I should have in order for the system to be stable. So to enjoy a good gain margin, this is what I should have. Okay, so this system, it has definitely a negative gain margin the way it is. Now what about the phase margin? So we go from here, now we go down and we measure the phase. Remember, this is the minus 180 line. So the phase margin is, this is the phase margin. This positive phase margin or negative? Negative. This is the phase margin negative. It is below the 180-degree line. So the system is unstable, and therefore the system is unstable the way it is, okay? And we have to do something about it. Okay, now this is how we define the phase margin and the gain margin, okay? So if I go back to my slide, okay, so this is my slide, the gain margin and the phase margin, we have to find the phase margin. Now the bandwidth, so the phase margin is 180-degree minus the phase angle of the transfer function. So whatever the phase angle of the transfer function, this is the phase margin. Now, what about the bandwidth? The bandwidth is the we take the transfer function, which is the closed loop now transfer function. G is the closed loop transfer function. We draw the minus 3 dB line, and the minus 3 dB line, the intersection of the minus 3 dB line, which is a constant line, with the magnitude plot gives me the bandwidth frequency, omega bandwidth. Okay. And omega bandwidth, we find it that it is between the crossover frequency, gain crossover frequency, and twice that value. So this is the range of the bandwidth. Okay.
Sir, is there an explanation for the minus 3 dB?
Well, the minus 3 dB, we said it last time. This is when the magnitude equal 1 over square root of 2. The magnitude 1 over square root of 2 is, gives me in dBs minus 3 dB. Okay. The last thing that what observation on the frequency response, it is disintuitive, physically disintuitive than the root locus. Okay, so the root locus, if you want to understand the physics of the problem, it helps you better. But this one, the advantage of this one, it is easier to draw. It is a lot easier to draw than the root locus. Okay, so now what we have. So if we want to look at the gain across, at the phase margin and gain margin from the Nyquist plot, what is Nyquist plot again? Do you know what is Nyquist plot? Real, imaginary versus the real plot of the transfer function, right? Okay, so it is like the body plot. Instead, you're doing in the body plot the magnitude versus frequency and the phase versus frequency. You cancel the frequency becomes parameters, and you plot the magnitude versus phase. The magnitude versus phase. So the magnitude now is a polar line. The magnitude becomes the polar, and the phase and this is the phase angle. So if you do this, which is it gives you a nice understanding of the phase margin and the gain margin. So at the at the high frequency, this is where this is how the Nyquist will look like. Okay. So at the large frequency, the system magnitude goes to 0. At high frequency, at high frequency, the system magnitude goes to 0. Okay, and this is why you see with the increase of the frequency, the Nyquist plot goes to 0. Okay. Now here, this is interesting. The crossing of the negative real axis. And again, why the crossing of the negative real axis? Now because we are plotting the complex function. And remember what we are doing, 1 plus kg equals 0. So kg equal minus 1. So the kg equal minus 1, which is a complex quantity, this becomes very important. Okay, and so the minus 1 here is very important. If I am to the right of the minus 1, this is gain margin. This is the amount of gain I can increase before reaching minus 1. How can I reach the -1? By increasing the gain or by decreasing the phase margin. So if I can rotate this plot, as you see the dashed line here, I can rotate it. Okay, by reducing the phase margin, I can cross the -1, or by increasing the gain margin. So either way, I can the system can be unstable. So the system in the root locus, we can make the system unstable by increasing k, increasing k for a second order system. This is the root locus for a second order system, right? It's a plus, correct? So if I keep increasing k, what happened to the damping? It will decrease. Okay, it keep decreasing until it goes to 0, right? So if I can decrease the phase angle, so I can decrease the phase angle, or I can increase the gain. So I can reach the same situation by increasing the gain or increasing the decreasing the phase angle.
Sir, how do we decide to do the dash?
Decreasing the phase margin. So,
how do we decide to draw the dashed line from the one that's coming out of the one?
Well, this is by if you increase the gain, and if you plot this is at higher gain, this is at higher gain, this is at higher gain, and this is at higher.
I mean the other one.
Which one? This one?
Yeah.
This is the circle of -1 radius. This is the circle of -1 radius. And this is -1 radius, this is the crossover frequency. This is omega c, this is the crossover frequency, okay? So this is the specification. If you, I don't want to go into, basically I want you to focus on the body plots, okay? Nyquist plot is very useful plot, okay? But we can obtain Nyquist also from body. This is not extra information, it is the same information, but how you are showing this information, how you are presenting the information. Okay, so so this is basically what we have said before. So the gain margin, therefore, is 1 over k, 1 over g of j omega at 180, the crossover, the phase crossover frequency, okay, and this is this frequency here. This is the 180 degree crossover. This is the 180 omega, the 180 degree crossover. Okay. So this is the gain margin. So if we calculate the magnitude here required to increase the gain to be at this value, and this is again, you have to understand this formula. It is again 1 plus k g gc equals 0, right?
Yes, sir.
Yeah, okay. Because we are talking about the magnitude. This is the k. The k in this case, it becomes k. Tell me, k. What is the value of k here?
-1 over g.
K is equal -1 over g gc. And if you take the magnitude, then k, the gain margin, this is the magnitude, is equal 1 over the magnitude of g gc at omega equal 180, where the phase is 180. Where the phase is 180. And the gain margin is the it is the okay, we can in dBs, this is the gain margin value in dBs, okay, and basically that's it. The phase margin now, it is the gain, it is the value of the phase of the system at omega crossover frequency. at omega crossover. Remember that this is the phase condition for the system. Okay, this is the phase condition for the system. And when the angle is 180 degrees, the imaginary part is 0, and the real part, okay. So this is the imaginary part will be 0, and this is how we define the phase angle. Okay. Yes.
We get the gain margin from the product of dB. Do we leave it in dB or do we have to change it?
The gain margin, you can write it dB. Okay, you can write it in dB. You have to use the units. Okay. If you are asked what is the value of the gain, you have to convert it from dB to actual value of the gain. And this is simple, right? Yeah. Now here we have, we want to differentiate between the body plot for a closed loop system and for open loop system. Okay, so the body, this is the system, right? L, this is the loop gain. L GCG is the loop gain. And in this case, for a unity feedback system, and we are working with a unity feedback system, this is the forward path gain. The forward path gain. And this is the open loop transfer function, right? So the open loop transfer function, N is the open loop transfer function, and I want to use it as such, to name it as such. So the open loop transfer function, the blue line is the open loop transfer function, body magnitude plot. The red line is the body magnitude plot for the closed loop transfer function, for the closed loop transfer function. And note that the magnitude at the high frequency is not changed by the closing the loop at the very high frequency, because the system acts as a filter. Okay, and as a filter, the low pass filter. So it will attenuate the response. Okay, and here, what is this? Do you know what is this? Anyone? I'll give you 10 points on your exam. I'm almost fine. Yeah.
The sensitivity.
What is the sensitivity? It is the sensitivity. So you got 87 now and 89. This is the sensitivity. What was the question?
That's why you didn't get both.
Well, what does this represent? The green line here. What does it represent? The green line is the S1 over G, 1 over 1 over 1. What is sensitivity? How this relates to the error for unity feedback system? How this relates to the error transfer function?
How the error changes when you change one of the parameters.
Yeah, this is the error transfer function. Right? This is the error transfer function, isn't it? For a unity feedback system. If you write the error, what is the error? What is the error? It is R minus Y, which is R times 1 minus Y over R, which is the error transfer function now. The error transfer function, so the error over R, this is the error transfer function, correct? Right? What is the error transfer function? It is R, it is 1 minus the Y over, which is L, over 1 plus L. And if you do this, this is 1 over 1 plus L. Right? So this is the error transfer function for a unity feedback system, right? This is the error. So the error, this is how the error behaves, okay? How the error behaves. So the error transfer function here. This is what is the system? We have minus 40 minus. This is 1 decade, okay, and this is approximately. If I extend it here, it is more than 2 decades. So this system is second, or it is type 2 system most likely. This is type 1 system. Type 1 system. For type 1 system, what is the error? What is the error for a type 1 system? For a constant
the velocity.
Zero. KB is infinity. KB is infinity, right? And the error therefore is 0. Now, this is minus 50 dB. Now, if you go here, this is minus, God knows how many, okay, it's minus 1 trillion, etc. So this is almost 0, right? So as when you go in the frequency, to a lower frequency, up to 0, okay, so let's suppose that this is 0.1. So there is 0.01, then 0.001, then 0.0001, and so on, and you keep going until 0. So this is minus infinity, right? Minus infinity, and minus infinity, this means 10 to minus infinity, right? So this is 0. This is 0. So the error is 0 in this case for a type 1 system, because this is type 1 system. The slope is minus 20 dB. How did I know it is minus 20 dB? Because this is approximately, if I extend the slope here, this is approximately 2 decades here, and we are getting 40, approximately 40. So this is 40 dB, 2 decades, or 20 decades, okay, minus 20. So this is type 1 system, and I know that type 1 system, the error should go to 0. Okay, the steady state error, the error to a constant input. Constant input means low frequency. Okay, very low, 0 frequency. Okay, so this is what we have here. So this is the difference between open loop, closed loop, and the error transfer function. Okay, or the sensitivity of the system. Okay, so okay, so let us move on.
Sir, what is the red line again?
The red line is the closed loop transfer function. This is the minus 3 dB, and here we get what? This one, what is this frequency here? What is this frequency?
Crossover.
Omega bandwidth. So this is the minus 3 dB. So the minus 3 dB, we get the bandwidth of the system. The bandwidth of the system, Zain. Yes.
So regarding the last, the mean curve,
Mm-hmm.
the frequency goes to 0, that's for the error function?
As you go here, yeah, the magnitude. The magnitude will go even smaller in dBs, right? Minus 50, minus 60, whatever, right? So as the frequency goes to 0, omega goes to 0. This is omega goes to 0 in this direction. This will go to minus infinity. Okay, goes to minus. This means 10 to minus infinity. 10 to minus infinity is 0. Okay, so this is what it means. But if the input, for example, the frequency is around this value here, okay, let's say this is 0.1, this is 1, and this is 10. Okay, if the frequency here 2, 3, 4, if the frequency is 4, this is the error. So we can see the error. It is around probably minus 20 dB. So it is 0.1. Okay, so it depends on the frequency. We'll see the error. Okay. This is the slide from the book. I think it has, this is the slides I took from the course website, the book website, okay? And I think if this is in the book, the way it is wrong, okay? Here, this This is the crossover, the frequency crossover, omega C phase crossover, omega CP. This is the phase crossover. The phase crossover, we get the the gain margin. So this is the gain margin.
So in this slide, I think the crossover is at 90 degrees. No, that's the correct.
This is the correct one. I am doing the correct one. This is the, huh?
They're saying minus 90?
No, minus 180. This is minus 180. Well, they cannot assume minus 90. How come to?
You said it's wrong.
Yeah, there is a problem. I don't have the book, but if this is the book, then there is a problem. This is a positive gain, because we need to increase the gain to make this pass through this point. We need to increase the gain. Okay, so there is a good reserve in the gain. Now the phase margin, okay, is this the same figure in the book? Huh?
No, it's not. It's not.
Yeah. Well, the phase margin, we look at the gain crossover. This is omega gain crossover, okay? And we drop a line here, and we measure the phase. So this is the phase. So this is the phase margin. This is the phase margin. So the phase margin in this case is a large phase margin, assuming this is the zero phase, okay? Or if I want to say okay, this is the 90 degree minus 90 degree phase, then the phase margin I have probably around 100 degrees. Okay? Well, that's good phase margin for the system and good gain margin in this case. Okay, so that's very healthy. Well, the best is to have a phase margin around 60 degrees. Okay. Well, this is minus 90. Okay, the phase margin is 180 minus this phase. Okay. And so the phase margin here around, let's say, this is 80, right? So we have a phase margin of 100. Okay? Now, let me bring your attention to this. Okay, when we did the frequency response, we used the three approximations, right? The low frequency, the high frequency, and the middle frequency, right? Correct? This is how we did plot the gain and phase of the system, the magnitude, the body magnitude, and the phase angle, right? Okay, so we let the frequency go to 0, we let the frequency go to infinity, so we got the asymptote. And in the middle, we say, okay, let omega, this is the frequency ratio we want, and let us look at the middle. So here, this is summarizing this. What we did, we want to see now how the low frequency relates to what in the system response. The high frequency relates to what, and the middle frequency relates what is the relation. What relates, for example, to steady-state performance? Yasmin, what relates to steady-state performance? Steady-state performance, how you obtain that? Yeah, and the frequency, I mean, how you steady-state. When omega goes to 0, when we talk about step response error, right? The step response error. The step response, it's a constant. It has 0 frequency, right? Okay. So when we talk about steady-state performance, we are talking about frequencies that are low. Yeah. Well, when time goes to infinity, right? So 1 over infinity, 1 over infinity, this is 0. So the frequency, when we go to low frequency, this is where we look at the steady-state performance. Yes.
middle frequency only a point or
It is a region. It is not a point. It is a region. Okay. Now we evaluated, for example, the magnitude and phase at when omega over omega t equal 1. Okay, just to get a point, so we can curve, we can by hand, okay, do the curve. But the mid frequency is a region. It's not only a point. And what is important about the mid frequency? What is the importance about the mid frequency? What do we extract from the mid frequency? Transient response. Transient response. This is when omega equal omega c, when omega is omega n. When you are at the corner frequency, this is where the transient performance is important. So if we want really to fix stability and transient performance, then this is what we need to address. We need to look at. Okay. So we need to modify this medium response or middle frequency response or around corner frequency response. This is where we want to go. What about the high frequency? What about the high frequency?
the difference between the number of poles and number of
Usually, well, as if you just remember, you need to, when you see a graph, you need to see information. When we did just a minute ago, we showed you the open loop frequency for closed loop. And okay, in the high frequency, the closed loop is the same as the open loop, right? Okay, there is not much. So the high frequency really, this is the controller does not do much, but we can see if the slope of the high frequency is large, this means that the system is good, and then if its disturbance rejection, its filtering abilities are higher. When you look, for example, at the higher frequency, you have minus 40 dB or minus 60 dB per decade. This means the magnitude will drop 1,000 times per decade. Right? Okay, 2 dB is 3 dB is 1,000 times, 2 dB is 100 times, 20 dB is, sorry, I said 2 dB. No, I mean 60, 40, and 20. Okay, 60, 40, and 20. 60 dB is 1,000, 2 dB is 100, 20, 40 dB is 100, 20 dB is 10. Okay, so you want the high frequency to have a high slope because you want the system to attenuate, reject any disturbances that high frequency. Any controller that results in amplifying the high frequency is not really recommended, but sometimes we cannot do that. Okay. So these are the okay. These are the how we see the frequency response. And now, if you go and work, for example, some of you work in oil and gas, and they have a rotating machinery specialist, static machinery, and if you are working in rotating machinery, this is what you work with all the time. You work on the frequency response. You will work with body flux, magnitude and phase, everywhere. You will deal with magnitude and phase. Okay? So this is what you see. These are the two plots that you will work with. It's like the chest-based specialist. Okay? So you work with only these X-ray diagrams. Okay, and you interpret them. The machinery, the test equipment provide you with body magnitude and phase, and you need to interpret. Okay. So now this is the low frequency. What we need to do the low frequency, the black line is the original system. And when we want to improve the low frequency, we need to increase the magnitude at the low frequency. Why we need to increase the magnitude at the low frequency? To reduce the error, because the intersection of this line with the magnitude is Kp, gives me Kp, right? So if I make it higher, I am increasing Kp. We explained this last time. I'm not going to go and explain it again. Okay. Kp is the value Kp, position error constant, is the intersection of the magnitude plot with the magnitude line as omega goes to 0. As omega goes to 0. So when I shift the magnitude plot up at the low frequency, this means I am directly what doing? Increasing the steady state error performance, improving the steady state error performance by improving Kp and W.
So you're moving the magnitude from up, right?
Yes, here the red line, what is, so we modified the frequency response, the controller modified the frequency response here, and the kind of controller that modifies the frequency response at the low frequency range is what? What is the controller that is meant to modify the PI and lag controller? The PI and the lag controller, they are, the main function is not to affect the middle frequency. You remember in the root locus, we did not want to, we got a transient performance, we want to stick there. We don't want to change. So we want to keep it the way it is. Okay? And this is how the controller, how this, these diagrams are not in the book. And unfortunately, they're not there. These are very important. Let you see the whole system, how, what exactly the controller is doing. So the other thing, if we improve the high frequency, here actually our objective is not to improve the gain here. Okay? Still the rollover, we are keeping the same dB per decade, right? Parallel. But what we are, what is the important thing that we are doing here? The intersection, we are moving it to higher frequency. So the corner frequency, the bandwidth, we are increasing the bandwidth frequency. So we are increasing the bandwidth frequency, and if we think of the bandwidth frequency in the time domain, what is the, when we want to increase the frequency response, what do you increase? Frequency response, the speed of response. Sorry, when we want to increase the speed of response, it is the rise time, which is approximately 2 over omega n, right? 2 over omega n. So what we are doing here, in order to make the system faster, we need to decrease the rise time, i.e. we need to increase the frequency, the natural frequency, and correspondingly, in order to do this, we need to increase the bandwidth frequency. Okay, so therefore here, this objective is really to modify the middle frequency response by shifting the frequency crossover, the magnitude crossover to higher frequency. So instead of having omega C here, we want to see omega C compensated here. This is omega C uncompensated. We want to have higher omega C. And this is, now here we are not affecting this controller. It is not affecting the low frequency. Unfortunately, what we are doing here, the high frequency, we are increasing the magnitude. We are not increasing the dB per decade, but we are increasing the noise level at the crossover. Right? Because we get, if I, for example, at this magnitude here, at this frequency, this is my original magnitude. So the system is attenuating the noise. And here the magnitude is, there is an increase in the magnitude by this much. So this is going to increase the noise a little bit. But we cannot do with that. And a complete system, sometimes you need a PID controller, so a controller to address the low frequency, a controller to address the high frequency, and therefore you want to shape the response at the low frequency, you want to shape the response at the medium frequency, and you get a system, you modify basically the frequency response the way you see it here. And this is what we call the frequency response shaping. Okay, and the controller does.
So why are the low frequency doesn't look similar when you pick up
What do you mean it does not look similar?
the line itself? The red
It's asking why do you choose this way?
Well, okay, why it is not, why we are keeping this line basically here? Why not just shifting the line, right? Why not shifting the line? Shifting the line, all the frequency response, you can shift it all together by simple gain feedback, proportional feedback. You shift, when we add gain, we shift the whole frequency response up and down. But this is this will result into changing the middle frequency, right? Okay, and sometimes we want to keep this. Okay, we don't want to change it. Okay, and so there are cases, many cases, most cases actually that we cannot do this. Okay, in the system we want to get the desired performance by doing this. So we want to keep some range the way it is, and we want to improve basically the error performance, and we want to do some adjustments either on settling time or rise time or overshoot and so on. Okay.
the slope here will change.
Well, the slope will change. The controller will change the slope in the medium frequency. Suppose we are adding a derivative controller. A derivative controller, it adds a zero. So it adds a zero, so you have a 20 dB per minute increase, right? So does it add, so it affects it. If you add integral control action, it adds a pole at the origin. And a pole at the origin, this means that you are adding minus 20 dB line. So minus 20 dB line, it affects this also. So it depends, if you are doing again only, yes, it is parallel. If you are doing a PD, PI, PID, or lead, or lag, etc., you have to have the slope at the medium frequency would change. Yeah, that would change the performance of the system when, depending on what controller we are using, and sometimes we are using lead, lag, PID controller, also on high frequency. Well, we will come to this. Okay, we will come to this. Okay, so these are basically okay. Look here. Okay, so this is what we have here. We have our nice second order system, right? This is the system we have performance for. Our performance that we talk about is second order system performance. Rise time, settling time, percent overshoot, etc. We don't have third order system performance, fourth order system. We only have second order system performance, first order system. Okay. So here, what we are doing. Okay. Can you tell me what we are doing? Then what we are doing here, there is the blue line, this one here, okay, and this one here.
Doing the same thing.
We are adding again to the system. We are adding again only to the system. So this is, we have the system 1 plus kg equals 0. For example, we are doing 1 plus g equals 0 and 1 plus 10g equals 0. So this is, we are adding 1 plus 10g, for example, equals 0. So we are adding log 10 plus log g. Log 10 plus log g. Log 10 is 20 dB, so we are shifting everything by 20 dB. Or I am just moving down the 0 dB line by 20 dB, right? Okay, so what we have here, the original system, if you look at the original system, this is the frequency crossover. This is the magnitude crossover frequency, okay? This is 10. Here we have a phase margin of this much. Now if I increase the gain, this is the new crossover frequency.
Yeah, the lower.
And
What is the phase margin? Smaller. This is bad for the system, and this is the I used in the previous class this example, and you have to when you do control, you have to take the foot locus and frequency response at the same time to help you visualize what you are doing better. Okay, because this is the our second order system. Is simple, okay? So this is the second order system. I have a pole at the origin, and this is this second pole at S equal minus 2 zeta omega. So now, if you don't know how to do the root locus, as I have seen many, not able to do the root locus from the multiple choice, I have a problem with the pole at the origin and the pole just like this and different options. And many people selected the wrong one. Okay, so this is the root locus. So the root locus basically it goes toward this breakaway, and it goes here. Now what happened when I increase the gain from a value, let's say here, to a value here? What happened? This is the corresponding angle. We said this is the this is zeta 1, and this is zeta, this is zeta 1, this is zeta 2, and this is the corresponding angle. What happened to the phase here? Margin. This is the phase margin. What happened to the phase margin? It will decrease, right? As I increase gain, the phase margin will decrease, and eventually for a second order system, the phase margin go to zero, right? If I increase the gain too much, this can go to zero. Okay, so this is how I can see it, right? The right-hand plot is for the closed loop system, and you see for the closed loop system by increasing the gain, what we did for the bandwidth frequency. What is the bandwidth frequency, Ahmed? The minus 3 dB. Where is the minus 3 dB? You see, it is quite higher because this is a log scale. The original frequency around 1. It is almost 7. So the frequency, the crossover frequency changed quite a bit. Okay, and so I was able to increase it. Same thing here, the frequency did change quite a bit, right? So the frequency, when I increase the gain, what I am doing to the bandwidth, I am increasing the bandwidth of the system, but the system might get the damping can be very small and the system would be very asymmetric. Okay. Now we want to design using the phase margin and gain margin. We want to design now using the frequency response, and it has an advantage. The main advantage here that it is easier to plot the frequency response. But honestly, to maintain the critical understanding, the root locus gives you better understanding. It's very hard to grow, okay, and for a complex system, it becomes hard to grow. We thank MATLAB, Now, if you remember last lecture, I gave you the relationship for the phase margin and I gave you the plot. I showed you a plot, right? And the plot was something like this, okay? So the plot was for the phase margin. I showed you something here, and it curves and it goes like this. And I told you up to this, in this range, the phase margin is can be approximated as a line, this line. So this is the approximation here. So the phase margin for damping ratios between 0 and 0.7, okay, can be approximated by this relation, and you don't need to worry about anything. So you use what is the data, the phase margin over 100. You never go.
So again, 1.7?
1.7?
No.
Yes.
Why? I know what is sensitive, but why? Experimentally found it. It's 5% from
When the fact that the system energy dissipation is proportionate to the speed square. It is non-linear. The damping ratio, the damping itself signifies the amount of energy of the energy dissipation that is in the system, right? Okay. So when the damping ratio becomes high, the amount of dissipation becomes nonlinear. Okay, the curve is nonlinear. If you okay here above 0.7, the amount of dissipation becomes of the dissipation energy dissipation zeta becomes very large, and the amount of dissipation becomes high. And also you have to understand that here, no matter what, this angle can be only what? This the phase angle for a second order system goes to minus 180. So no matter how what damping you have, the phase angle goes to minus 180. In the middle frequencies, the curve is very nice, so it can be approximated by a line. And when you get the damping ratio very high, then it becomes not linear. Okay.
So, sir, zeta should not exceed 0.7, right?
Well, to use this relation, zeta can be any value, but to use this approximation, and for a system, for any system, we don't want to have too much energy dissipation. Because energy dissipation, what does it mean? Wasted energy. Wasted energy. You don't want the system to waste a lot of energy. So we would like to have the energy dissipation, that damping ratio, always reasonable. Okay, something that the system will not have too much overshoot, and also it won't have much energy dissipation in it. Okay, it won't waste a lot of energy. Okay, so this is what we want. Okay. So the amount of energy, the amount of damping, variable damping, most of the time between 0.6 and 0.7. 0.6, all control system you look, it's between 0.6 and 0.7. Okay. It depends on the application. Oh, okay, so let us look at how we design with the frequencies, in the frequency response. So we have the phase margin. The phase margin, what does it represent? What does it mean, the phase margin? How much damping we have, right? How much damping? Remember, zeta equals phase margin over 100. So let us use this formula. Okay. So phase margin is how much damping. Okay. So and we learned that if we want to design a control system, the first thing we do, we close the loop. The second thing we do, we adjust the value of K. If our specification is met, then it is fine. If it is not met, we will find whether we want a controller which is a lead controller or a lag controller, and we inject it. Okay, and we check this. So this is the procedure. Now here, this is the design procedure in this case. We're using phase margin. So we draw the body plot, magnitude and phase for the uncompensated system. For the open loop system, we draw the body magnitude and phase. Now we determine what is the phase margin required for the system, Ahmed. We determine what is the required phase margin in the system. So for example, if the phase margin required, let us go back here. If the phase margin required for me to have, this is 120, I want to have 60 degrees. So this is the phase margin here. This is so I look at the magnitude, and I find that this magnitude at this frequency, the magnitude is above the 0 dB line by probably 10 dB. So I need to reduce the gain in the system to bring this to to 1 dB, to 0 dB, to one magnitude of 1, which is 0 dB. Okay, so I need to adjust the gain reduces. Now, if I reduce the gain, I go back and check my steady state error. Is it still acceptable or not? So the first thing, we satisfy the damping. We want the system stability to be fixed and to be as we desire. Okay, so once we do this, we find the frequency on the body phase diagram that yield this desired frequency. We find that we just know what is the frequency. Okay, and we we can change the gain to bring the magnitude of clock to 0 dB, just as I showed you. Yes.
So you said you wanted to increase the phase margin, right? Aren't you automatically increasing the damping?
Well, yes, we are increasing the damping, and here, this is my system. This is the open loop system, the blue system. Okay, so now this is my phase margin. So the phase margin, really, I want 60-degree phase. So 60-degree phase margin, this is here. So the frequency, this is the frequency, and the frequency here, this is the frequency 0.2, 0.3, probably 0.4. Yeah, so this is the 0.4. Now at 0.4 here, I want to, at 0.4, this is the magnitude. This is the magnitude. So I want to bring this down to a 0 dB line. Okay, so this is how we do it. Okay, so the gain, I need to adjust the gain to achieve the appropriate damp. Just like when we did here. So my desired roots here, suppose my desired root from the damping, I got the damping of 60 degree. So 60 degree, I draw the 60 degree, this is the intersection. Okay, at the desired gain, at the gain I have, for example, the root locus is here, or the root locus is here. So I want to increase the gain just to bring it here, to this point. Okay. Well, it depends. Okay, now if I am keeping the same root locus, yes, it is a lag control. If I don't have any other specification, it's just damp, okay, which is overshoot. Damping, it means overshoot. I have only overshoot specification. So let us go to example. This is example 11.2 in the book. So here, and I want you to pay attention. Here, it says the problem, given the system in this figure, this is a motor that we are driving a load with a DC motor. Okay, so it says that the body, use the body diagram to design a lag compensator to yield 10-fold improvement in the steady state error. We want a 10-fold improvement in the steady state error. Anyone has the book? I think I did copy the wrong text. Okay. This is on the lag controller, but I want just first thing to know is just proportional controller, and proportional controller should be example 11.1. Yeah, example 11.1. Yeah, example 11.1. I want example 11.1. 11.1, it is, forget the text here, I'll remove it from the slide. Problem for the position control system shown in figure 11.2, find the values of the preamplifier gain K, to yield 9.5% overshoot. In the transient response for the step input, use frequency response method. So here we did not address any steady state response. Only overshoot. So what we need to do? Here, we find from the overshoot, we do the body plot. I did it with MATLAB, not the figure in the book. Okay, it's clearer.
we first check the overshoot. Overshoot corresponds, we go to the overshoot zeta relationship, we find zeta. Zeta is 59.2 for zeta, sorry, 60.6. Zeta 0.6 phase margin equal 60, right? Because phase margin equal 100 times zeta. 100 times zeta 60. So forget about 59.2, this is 60. Okay, and I don't, in your calculation, don't bother to put anything after the decimal. You are working with decimals only for 0.1, 0.2. Just need two significant figure always. Okay, so you don't need to keep more than.
So this is what you learn from the master?
No, this is from the exact relationship. You know, you will get the formula for the percent overshoot versus damping, and for the phase margin damping relationship. This is this formula here. I just showed it to you. This is this formula. This is this formula here. Okay, so we don't want to use this. We use the approximate one. Okay, okay. So this is what we have. So what we have here, we find the phase margin. Then we locate the frequency with the required phase. With the required phase, this is the frequency with the required phase. It's 15 radians per second. 15 radians per second. So now the magnitude must be raised to be equal 1 at this frequency. The magnitude must be modified to be equal 1. Raised or reduced, it should be equal 1. We look at the graph and find out. Now the magnitude, okay, so in this case, if I look at the, this is the, I think the phase, the original system is the blue line. The original system is the blue line. So if I want to know what is the what was the angle we said we need 60 degrees, right? 60 degrees. If I want to look at 60 degree reserve, this is 90 and 35. This is 45. So 45. If I want, it is approximately somewhere here. So somewhere here, this is the frequency, and the frequency here.
60, right?
60 degrees. So this is the 180 degree line. We need 60. This is how many degrees? This is 45. 45. And this is this one is also 40. This whole thing is 45. So 45 plus 20.
22.1.
So it is somewhere here actually. So we are here. We are here. So this one, if we project it here. So this is 10 and this is 20. So we are at approximately whatever. I will use the middle frequency. Middle frequency between 20 and 10 is 15 radian per second. So I am happy with 15 radian per second. I go find the amplitude at 15 radian per second, which is at the middle. Let me use the middle of this range. So the middle of this range, what is the magnitude? The magnitude is approximately 20 dB, right? It's approximately 20 dB. So, the blue line, between the blue line and the 0 dB line, at this frequency, it is approximately 20 dB. 20 dB. So I need to increase the gain by 20 dB. Increase it or decrease? We need to increase the gain by 20 dB. We need to increase the gain by 20 dB. So let me do this with you and using MATLAB, so you can see what we are doing. Okay. Okay. So let me go to MATLAB and do it. So this is our block. Okay,
if you want, maybe I can do the I can plot the system here. So the system, just for your reference, what we are working with. So we have a K, we have the amplifier gain, which is 100 over S plus 100 over S plus 100, and then here we have the motor, which is 1 plus 1 over S plus 36, 1 over S plus 36, and then the integrator to get the position. So this is it. So this is the system. So if I want to basically make this over 100, so this would be 1 over, so this is, we can write it in this form, and here we can write it, this is 36, and I get it here 1, and this is 36, so this is 1 over 36, right? 1 over 36. So, okay, and this is 1. Yes.
Let it be 0.01.
Why? This is 100 here, so, and there's 100 in the numerator, so, okay. Okay, so this is the system. Now, if I do it, okay, this is my transfer function. You see it here? This is my transfer function. Okay, so if I do body plot of this transfer function, so this is the body plot, and I can just make the units. This is minus 270, just to, okay, and this is minus 90, minus 2. The magnitude, sorry, the magnitude, let me be 40 to minus, limits to minus 100. And this is to minus 90. Okay, guys, okay, so we want to do the, let me just make it clearer, the scale, so you can see it, okay. Fonts, 14 bold, okay. Okay, and this is, okay, so this is my phase plot, the phase and magnitude plot. This is body plot. Okay, now let me check where the phase. Okay, the phase margin, we need 60-degree phase margin, right? So the phase should be around minus 120. So to have 60-degree. So let me check the phase. It should be around here. So around here, this is minus 119, and right, minus 1, which is close enough, and the frequency is 13.7, so around 14 degrees. So this is the frequency. Now, if I check here, the magnitude, approximately, we are talking about this point here. So the magnitude, this is the frequency, exactly same frequency, and the magnitude in dBs, this is around what? Minus point. Well, it is very close to 0, right? It's very close to 0 here for the plot that we have done, right? So this is very close to 0. The magnitude in dB is minus 0.576. We can find the exact magnitude. So here, huh?
It was 20, right? Before,
Slide.
In the slide, well, I did the slide. I might ignore the 100 in the slide. You see, okay. So this is what I have. So here, what we are getting, basically, this is the amount of magnitude that we need to add this amount of magnitude to make it this minus 0.576 dB. Minus 0.567 dB. This means a small magnitude that we need to add. Okay, for the to get this. Okay, so let me check. So this is I did the 100 here. Okay, so the 100 you have k time. So k times therefore k should be the one that brings the magnitude to this. Okay, so this is how we do it. Is this clear? Okay, is it clear? So suppose let me class time finished. Okay, well, just 1 minute. Let me just to divert from to show you a clear case. Suppose my phase angle that I came up with is 45 degrees. So 45 degrees, this means, okay, let me just delete this one. 45 degrees, this means that I am here at this point, exactly, right? When I am at this intersection of the phase line with this is 45 degrees. So 45 degree, this means that my magnitude is here. So I have at this I have 5.52 dB minus. Okay, so I need to add 5.5 dB to the gain in order to make this phase angle. In order to make this phase angle. Okay, so this is how much I need to add to the system. Okay, so now where we are going, okay, you have a long break and enjoy your break. What we have, the following. I will do the, by Friday, hopefully, Friday this week, I will post a recording of the lag controller and lead controller, and I will do them separately. Two different recordings, so the recording shouldn't be long, okay? For a design of the lead and that controller in the frequency response. Yes. I will do that. It will take time, but I'm probably tonight. I will try to sit on Friday and do it. Okay. So I will be able to do this for you Friday. Record it and load it. Okay. So please do listen to these recordings. And if you have any questions, you contact me. Okay. I don't want to put them on use the blackboard because I don't know where you are on Friday. I will just put the recording and I will try to elaborate as much as I can. Okay. Now you have two homeworks, okay, that you need to submit when you come back, and these are the final homework that you need to do. Meanwhile, your project should be submitted next Wednesday, so I will not accept anything beyond Wednesday. The project, progress report. The project progress report is next Wednesday. The project final report, I'm not going to postpone it any minute. Why? Because I need to grade it and put it on the system. Okay? So you need to be, okay, and I have the right to ask any group to come and present their project individually. Okay? So I can ask Ahmed, your time is this come and present this thing. And I will select this at random. I'm not trying to target anybody. Okay? So I will select people, those who are especially having attending the class very well,
they showed one interaction. I will select from those, okay, to see what exactly we are doing in this course, okay. And those who want to present, okay, especially the ones that come with a successful project, we will ask them to present, okay, and then we probably invite other people.
You will give them, so that the lesson is given. They
When they did a great project, they did a great project, which means that they did the analysis, they did the project hardware, and they presented individually evaluation. Okay. So I have a case for the group that, for example, on the project 25, 25, and 25. Okay. So you can, the key is to present to me, and I ask you questions about what you have done. Okay, so this is the.
And have a nice break.
have a safe flight, yeah.
Thank you. بس أعطيني دقيقة بس.